Music. Music is one of the few things that is common on the entire planet. Throughout time, music has been an important part of life, from China 9,000 years ago to ancient Egypt in the Middle Ages, and all the way to modern time. Music has been present in most cultures. And today, you can see music anywhere you go in the world. Since its early days, music have evolved, but the way we find and discover music have changed even more. I would like to take you all on a really short journey from the first evidence of music to modern time and explain how the discovery of music have changed. Since all people of the world, including the most isolated tribal groups, have a form of music, it may be concluded that music was present in the ancestral population. Music have in fact been in existence for at least 50,000 years, and the first music was invented in Africa. Music was at this time invented and shared in the tribes. It took many millennia before music was spread past tribes. Music was contained in smaller population until musical notation were invented around 4,000 years ago. But with notation, people could experience and discover music from far away. With musical notation, mankind could now write down their songs, but the written word itself were for the rich and for the holy. One of the biggest contributions for sharing music has absolutely nothing to do with music. And that's the Gutenberg printing press. The first century after the printing press was invented, 12 million volumes were created. But still, people would need someone who could sing or play an instrument in order to discover and hear music. If you could neither, like me, you could not experience music at home. In the 1600s, that changed with the invention of the music box. You could now sit at home and listen to music. Unfortunately, the music boxes were expensive, and only the rich were able to experience music at home. At the end of the 1800s, a brilliant man, I think most of you have heard about, Thomas Edison, invented a phonograph. Now the middle class could also enjoy music at home. Vinyl. This is actually something we had at home when I was a kid. Who here in the audience have a vinyl player at home? That's like half. That's awesome. It's quite retro nowadays. It's surprisingly old as well. Invented in 1901. Vinyl was really huge for music. With vinyl, it became so much easier to switch to new songs and also a lot more affordable. About the same time, radio became essential for the spread of music. Early uses for radio were maritime, were sending Morse code between ships and land. But after World War I, they started commercial radio, containing not just news but also music. Now music is spread faster and further than ever before. Radio and vinyl were the main sources for music for the next 60 years or so. In 1979, the cassette player known as Walkman were created by Sony. All of a sudden, you could walk around, take a run, sit on the bus, while listening to your own music. From here on out, music really began to take a great part of people's life. It is impossible to talk about the way people discover music without mentioning the biggest disruptor of all time, the internet. In 1993, the first free, high-fidelity online music archive of downloadable songs on the internet were launched. 5 years later, an early music store business model were created. It allowed visitors to visually search through a jukebox-style catalog of 300,000 songs, selling songs for $1 and albums for $10. Now, for the first time, you could sit at home in your underwear and discover and buy new music without leaving the apartment. The next internet disruption was launched in 1999. Napster was released as an unstructured, centralized peer-to-peer system, requiring a central server for indexing and peer discovery. It is generally credited as being the first peer-to-peer file-sharing system. 2 years later, Apple and Steve Jobs finally joined the music industry and created the iPod. Now you could have 1,000 songs in your pocket. I remember that it's only 22 years since people first could bring songs in their pocket with the Walkman. Combined with the massive power of the internet, people literally could download and bring any song they wanted in their pocket. This is something that was unthinkable only 10 years earlier. In 2008, Spotify was launched. Now you could legally listen to almost any song in the world, either by accepting commercials between songs or by paying a monthly fee. For $10 per month, you could listen to any song in the world. It had never been as easy to discover new music with integrated top list in the application. With the introduction of the smartphone, you could now bring the world library of music anywhere where you go. And finally, in July 2015, Spotify launched Discover Weekly, a feature which uses AI to suggest songs that Spotify thinks you would like based on your music habits. That was a quick history lesson. The way we discover music have changed so much the last 100 years. And today, we will teach you how you can create your own music recommendation system at home. So real quick about ourselves. We are 3 consultants working for a Nordic consultant firm named Knowit, working from Oslo in Norway. My name is Lehn. I'm a technical team lead and a manager at Knowit. Currently working on a new sales and ticket solution for public transportation in Norway. For the last 2 years, I've been passionate about AI and machine learning. I have done both professional and personal projects using machine learning. And my personal dream project is to create an AI that can beat me in Mario Kart, but I have not had time to do so yet.
It's not really that hard to beat you in Mario Kart,
Okay, yeah. So my name is Malte Anderson. I'm a software engineer currently working on algorithms to optimize ticket prices for the Norwegian railroad company NSB. I wrote my master's thesis at the Norwegian University of Technology, where I specialized in artificial intelligence. Today I'm head of Artificial Chapter, which is an internal group in Knowit Oslo, for gaining and sharing knowledge about artificial intelligence and machine learning. Fun fact about me, I wasn't wearing pants when we took this picture.
So my name is Manu, and almost everything Malte just said applies to me as well. I mean, I was wearing pants when taking that picture, but otherwise, I also graduated from the Norwegian University of Technology, writing my thesis about artificial intelligence. And I'm the other leader of Artificial Chapter in Knowit. And currently, I work on the same project as Joachim.
This presentation was originally created as a workshop, meant as an introduction for machine learning. But we have tried to convert this into our presentation, which is also an introduction to machine learning, using a specific practical problem to solve. Today's agenda is an amazing mix of different machine learning algorithms. We will have theory sections before having a demo of that subject. Thus, we will be switching between theory and demo several times. We will start by introducing core concepts in machine learning to make sure that everyone in the audience is on the same page. We will briefly explore subjects like features, labels, and feature engineering. We're going to quickly explain the Spotify API, which we've used, and feature which we'll use in today's demo from the dataset. Then we will start with the real good stuff, talking about supervised and unsupervised machine learning, before moving on to clustering. We will explore K-means, one of the most popular clustering algorithms, and of course show you some code for all of this. Around this time, we're going to take a half an hour break. I think we all need some coffee to soup in all the machine learning. Then after the break, we'll kick off by pursuing more awesome algorithms, starting off with dbScan, exploring both basic theory and concept, as well as a demo. We'll follow dbScan up with hierarchical clustering. Then we will move on to one of my favorite algorithms, support vector machine. We will finish off by having a session about neural networks, but don't worry, we will not dig deep into the math here. Some math, but not deep. And finally, we will see our hopefully fantastic music recommendation system in action. And hopefully it's going to give us some decent recommendations. At the very end, we will give a quick summary and explain how Spotify themselves have created the actual Discover Weekly.
Yes. Okay, thank you, Joachim. First off, I want to mention that when we say participant or user, we're talking about people who participated in the workshop that this talk is originally based on. That being said, I'm going to introduce some machine learning and the difference between machine learning and artificial intelligence. So artificial intelligence is a broad term, usually referring to getting a machine to do something intelligent. That's also the goals of machine learning, but machine learning also has some additional properties. That the algorithm uses examples or data to learn from and is not explicitly programmed. Therefore, you can think of machine learning as a branch of AI that deals with getting computer models to learn from data. Since machine learning is so heavily based on data, processing it before feeding it to an algorithm is often alpha and omega. However, data processing and dealing with data can be a very expensive task. So before we talk about pre-processing, we need to introduce some terminology so everyone is on the same page. And two important terms are features and labels. So let's look at an example here. On the left, we have a table with some input data, and to the right, we have something that we want to predict. The input here is the make of a car, is the model, is the mileage of a car, and is the year the car got produced. And what we want to do is we want to predict the price of this car. So the table on the left here is called the features, which is the data we put into a machine learning algorithm, and on the right we have the label, which we want to predict. Another important thing to mention is that we often talk about dimensions of data, and it's simply the number of columns in the feature table. So here the data is 4-dimensional. And if we remove a column, it gets 3-dimensional. However, we can see that the features in this table is not really that good because the model is kind of redundant based on the make of the car, for instance. So we have to kind of address this. And that process is called feature engineering. Feature engineering is the process of using domain knowledge of the data to create features that enhance the performance of machine learning models. Feature engineering is fundamental to the application of machine learning, and it can be both difficult and expensive. So when you're doing feature engineering, your goal is to make sure that the data you provide an algorithm is of the highest possible quality. All data you put into a machine learning algorithm should be relevant for the problem you're trying to solve, and it should also be non-redundant and non-biased. Feature engineering can be kind of divided into feature selection and feature extraction, which I'm going to talk about soon. But an important note to talk about first is that feature selection and feature extraction both reduce the dimensions of the data. And reducing data, the dimensions, both has positive and negative sides. So let's look at that first. So when you reduce the dimensions, you speed up the algorithms that you use because it has less data. It needs less data to process. Then you also reduce the space used by the data, and this means that you have less processing power needed. It's also kind of hard to visualize highly dimensional data, but if you reduce it down to 1 or 2 or 3 dimensions, for instance, it gets pretty easy to visualize. Sometimes reducing dimensions to visualize helps humans to understand algorithms better, it helps understand the data better, or it helps explaining others the data or algorithm. However, you should be aware of some things, though. Some people reduce the dimensions of the data just to prevent overfitting. Overfitting is when the algorithms learn the training data too well and can't generalize into unseen data. The idea is that, let's say you have 100 features in your data set and you reduce it down to 50 features, the model will be less likely to overfit. However, you might be throwing away potentially very important data and your general performance might decrease. You should be careful about that. So feature selection and feature extraction. Feature selection is the task of choosing relevant data for your application and making sure, as I said earlier, that the features are informative, non-redundant, and non-biased. It's a dimensionality reduction process because you start with a set of raw variables and always choose a subset of these raw variables. Feature extraction is also a dimensionality reduction process, but it derives completely new values given the raw variables in your data set. So let's look at feature selection first and start with a couple of examples. Firstly, having redundant features in your data is exactly that. It's redundant. It uses unnecessary space and increases runtime on algorithms, and therefore you want to remove them. So let's look at this example. If you have some data with the weight, height, and the body mass index, or BMI, who is extracted from exactly only weight and height, it is redundant to have it, and you should probably just remove it. and it won't hurt your performance at all because you're not losing any data. Another example is that, let's say you want to make a music recommendation system, and you have 3 features to work with. One of them is danceability, which describes how suitable a track is for dancing. The other one is energy. It's how much energy there is in the song. For instance, heavy metal has high energy, and more classical music has a lower energy. Both of these features has a number between 0 and 1, where 1 is the highest. And then you have a feature that's the temperature in Greenland. Now, I don't know about you guys, but that's pretty irrelevant when I determine what songs I like, so you should probably remove all of these irrelevant features. The last examples I'm going to have about parking ticket complaints. So let's say you want to try to find out if a parking ticket complaint should be granted or denied. And this is the data you have to work with. Now this can, some unfortunate things can happen when you have data like this. It can, for example, the machine learning algorithm could, for example, learn that all Audis should get their complaints denied. Or it can learn that all Audis in Antwerpen should get all their complaints denied. Or it should learn that all male drivers in Antwerpen driving an Audi should get all their complaints denied as well. It's a little bit more tricky to deal with data like this, but also removing it could be one way to solve it, or at least address it in some other way. How are these examples I've showed you guys? They're really basic, and the example was like at most four-dimensional. So what do you do if there's 1,000 or even many thousand features to look at? And maybe you're not even sure what all the features means. So there are algorithms for these problems. And typically a feature selection algorithm is a combination of searching to find new feature subsets along with some evaluation measure that scores the different feature subsets. The easiest algorithm for this is simply to try each possible subset of features and then find which subset minimizes the error rate of the model you're trying it on. But this brute force approach is not really feasible when the dimension of the data is too big. So you you can divide into 3 types of feature selection algorithms. There are wrapper methods, where we try to use a subset of features and train a model using them. And then based on inferences that we draw from the previous model, we can decide to add or remove features from our subset. So for instance, you're using some subset and you're training a machine learning algorithm and you get some results. Then you remove, for instance, one feature and you do exactly the same. Now, if the error rate goes up and down, you can then decide if you should keep that feature or remove it. In filter methods, features are selected on the basis of their scores in various statistical tests for their correlation with the outcome variable. So I don't know how familiar people are with this, but you can, for example, find Pearson's correlations with each feature and then see which ones correlates well with the output variable and then choose your features based on that. And then you have embedded methods, which kind of blends these. I'm not going to talk about that a lot now. So that was the feature selection part, where you simply find a subset of features that you can use in your machine learning algorithm. Feature extraction, on the other hand, as I said, it derives completely new values from the features you already have. As I said, it's also a dimensionality reduction process. And we use it in our model to reduce from 13 features to 2 features, so we can visualize it in 2 dimensions. So let's just look at how the principal component analysis, or PCA, works. As we can see on the example on the right here, we have a 2-dimensional space at the top and then 1 dimension beneath it. What PCA wants to do, it wants to find a single line onto which to project this data. So how do we determine this line? It's you just find the distance between each point, and the projected version should be small. So you want to try to minimize the distance from each of these data points, the crosses, and the green line. As you can see on the example, the green line then becomes, that's a 1-dimensional, because a line is 1 dimension. And you can see that the red cross is going to the far to the left, and then the black cross appearing, and then the green one, just like in the 2-dimensional data. There's a couple of things that's important to do before you use the PCA. The first one is mean normalization. We have to determine the mean of each feature set. And then for each feature, we subtract the mean from the value. So we rescale the mean to be 0. And then PCA can perform a little bit better. Another thing you have to do is feature scaling. Features can, for instance, have very different scales. For instance, like I mentioned, danceability. It is a value between 0 and 1. But if you have something also like the duration of the song, which I guess could be from 0 to kind of infinity, or a really large number, then you want to make sure that the values are rescaled so they have the same scale. Usually you have a number between 0 and 1. Yes. Okay, so let's talk about the data set that we are basing all of this on. So firstly, a data set is a collection of data that you use to feed your machine learning algorithm, and then you pray that the algorithm learns something useful from the data. A data set for someone creating a music recommendation system could be something like a collection of songs. More specifically, it could be a collection of songs that a user likes and a user don't like. And this is our case. So optimally, we would like the people who participated in our workshop to choose all the songs that they like and songs that they don't like. But actually finding songs that you don't like and finding between 1,000 or 2,000 songs that you don't like, that's actually harder than it sounds. So what we did is that we used the Spotify library. We downloaded a bunch of playlists. And we made it so that the playlists represent one genre. And one genre is represented with multiple playlists. And in each playlist, there's about 50 to 100 songs. So you can see, I just screenshotted a pie chart here. We can see the top left that we have a 60s folder, which is contains all playlists that is in the 60s genre. Now a user can then choose playlists instead of songs, and you only have to pick 20 playlists instead of picking 1,000 songs. Yeah. Then we have kind of downloaded one super playlist. It's really large. It's about, I think it's about 8,000 songs that we is representing all of the songs in the world kind of playlist. And this is because we don't really have easy access to all the songs in the world. Okay, so now a user has chosen all their songs, and we have a list of songs that we can recommend from. So how do we represent a song? It's because we need to compare them. For this, we use the Spotify Web API. When you query the API with a song, then it returns a set of features for you. In our case, it's going to be 13 features that we can use. I'm going to go more into details about that in the demo really soon. And then, as I mentioned, we used Spotify, which is a Python library that just wraps around the API, so we can just easily do it in Python. Okay, let me go into Mirror. Yeah, okay, so this is the first time you guys see the code. I'm not going to work with these ones right now. We're going to start with this one. So here's all the features and a description for the features. So you can see here, one feature is acousticness, which is a confidence measure from 0 to 1, whether the track is acoustic. And 1 is the highest. Then you have danceability, which I described earlier. A suitable track is for dancing. Then we have the duration of the song in milliseconds. The energy, which is also a measure from 0 to 1. Instrumentalness, and some other features. The key ones to look at now is the key one, is the key feature. The key the track is in. And the mode indicates the modality, major or minor, so it's either 1 or 0. And then you have the time signature as well. Because we're going to do some feature selection, and we're going to just simply remove the ones you think are irrelevant. All these ones I'm going to remove. Also the duration in milliseconds. I don't feel like that's important when I look at a song. And then here are all the playlists that a user can choose from. So right now we have the likable songs. Remember, we have to tell which songs we like and which songs we don't like. So you can pretty much just comment in and out here. So we have chosen to have some 90s song that we like, some metal songs, some classical. I'm going to comment these out for now. Some rock songs and some 80s songs. And the songs that we don't like are going to be hip-hop songs and electronic songs, some reggae and some R&B. Okay. Lastly, I just want to show that sometimes you can get some insight in your problem just by calculating easy statistics, such as average and standard deviation. So here we just have some code. I'm just going to go through it line for line. The total features are the features that we just chose. We have the likable songs. We take the likable songs. We get the data from them, the song name and the artist for all the songs. We calculate averages, and then we plot it. And then we calculate standard deviation, and then we plot it. And then the demo curse is hopefully not with us today. We can look at this. Okay, so here you can see the average of the chosen features. So by this, we can see that, for instance, our energy is 0.78, which is quite high. So we know we maybe like songs that have a lot of energy. We know that the tempo we like is maybe around like 124 beats per minute. Another thing to see here when you look at the data like this is that all of the scales are kind of different. The tempo is beats per minute is in a different scale than loudness. Loudness is in a scale of -60 to 0, where 0 is higher. And loudness tells something about the loudness in the track. Yeah, so you want to make sure that these are in the same scale. Usually you do it by choosing a number between, or a float between 0 and 1. Then we can also just look at the standard deviation really quickly. That tells us something about how much our the features are varying. So you can see that if we assume a normal distribution of the data, 68% are going to be between. So the average of danceability was 0.51. And then if you go 0.15 to each direction, about 68% of all the data is going to be between that range. So this tells us something about how much variety we have in our music tastes, I guess we can say. Yes. Okay, and it is you.
Thank you.
Thank you.
All right, I hope you guys are still with us. Now that we know about features and labels, we can get into how to use this for machine learning. So today we're going to use methods from two categories of machine learning, namely supervised learning and unsupervised learning. Supervised learning is used for predictive modeling. Given a set of input features, you want to predict a certain outcome. There are many different algorithms which differ in their approaches to learning, but they all have in common that they intend to learn a target function which can map input variables x to an output y. This function is based on examples from the domain you want to predict. The first step in machine learning concerns the data. That's why we've been talking a lot about data and data processing. To train a machine learning model, you need a data set of examples from the problem space. And it doesn't really matter if you have a carefully constructed machine learning model if your data is useless. So you've seen this before. Say you want to predict the market value of cars, right? So you need a data set describing different individual cars through a structured representation. And this representation can be the make, model, mileage, and the year of the car. And additionally, we talked about labels. We need each sample to be labeled. What was each car actually sold for? And this is why it's called supervised learning, because you act as a guide for the learning algorithm by providing the correct answers to each example. It's common to say that the more examples you have in your dataset, the better. But you should also remember that, like, for example, if you have a lot of examples of Audis from '95, then your algorithm will have a hard time making predictions for BMWs from 2015, right? So what's most important is that the dataset covers the problem space as much as possible. This often implies, though, that the larger the dataset is, the more likely it is that you cover the problem space. So next, the training set is fed to the learning algorithm. So based on the examples of the cars and the correct labels, the learning algorithm tries to capture patterns to approximate the function of predicting the market value of cars. So our goal when training the model is for the model to be able to generalize the problem of predicting the price in such a way that you can then use the trained model to predict the market value of any car. Cars that it hasn't seen before. There are many different algorithms for supervised learning, but today we're going to train a couple of classifiers using the support vector machine and artificial neural networks. Another branch of machine learning is called unsupervised learning. Unlike with supervised learning, we now deal with unlabeled data. Based on the attributes of the data, unsupervised learning can be used to understand the data and the structure of the data. And since there are no labels, there are also no correct answers. So to assess the quality of the model, you'd have to analyze the results that it produces. We're about to go more into what this means, as we're going to use clustering on song vectors. Today, as you saw, we're using Python, and we're also going to use the scikit-learn framework for the traditional machine learning methods. And for the deep learning part, for the neural networks, we'll be using Keras, which works as a wrapper around Google's TensorFlow library. And we're using Keras because it's a little bit more user-friendly. It's easier to use than TensorFlow.
Yes, so clustering. Clustering can be considered one of the most important unsupervised learning problems. And it deals with finding structures in a collection of unlabeled data, like Manu said. A loose definition of clustering could be something along the line of the process of organizing objects into groups whose members are similar in some way. A cluster is therefore a collection of objects that are similar between them and then dissimilar between objects belonging to other clusters. Cluster analysis in itself is not one specific algorithm, but is rather a problem to be solved. It can be achieved by various algorithms that differ significantly in their understanding of what constitutes a cluster and how to efficiently find them. And we're going to look at 3 different clustering algorithms today. So how can clustering help you make a recommendation system? Well, by putting similar songs in a basket, then different baskets with different similarities are going to get created. You can think of it a little bit like genres. In one basket, you kind of put all the rock songs, while in another basket, you put all your classical music. And then by analyzing the music a user is listening to, we can recommend similar songs to the user because we have different baskets where each basket contains similar songs. So for instance, if a user is listening to music with a high danceability score and a low energy score, we hopefully have some basket that can represent this, and we can choose songs from that basket. So today we're also going to visualize the songs in 2 dimensions, so we can kind of see which songs are similar and which are not, according to PCA and Spotify API. And then we will show you 3 clustering algorithms that clusters the data differently. Yes. So when we say similar songs, how do we really know if they're similar or not? So let's look at an example here. Let's look at our music recommendation example. So we have 2 songs, and we want to figure out if they're similar or not. The first thing you do is you have to somehow represent the songs in a number format, right? And that's what the Spotify API does for us. We just query that, and we get some numbers back, right? So now there are multiple kind of ways to find the distance between 2 songs. But the most used one is probably the Euclidean distance. It's a pretty simple formula. For each feature set, you just take the difference and then you square it and then take the square root of it, of the sum of those. So just look at a quick example. Let's say you have 2 songs, song A and song B. Song A has 0.3 danceability score and 0.2 energy, and song B has 0.7 danceability score and 0.8 energy score. Then you simply plot it into the formula, and you get that song A and B are 0.72 in similarity, where if they're exactly the same, the number would be 0, and the higher away from 0, the more dissimilar the songs are. So yeah, just one last example. Let's say that these are all the songs in the world. We can now cluster this data set. We can analyze the user's music taste and see which cluster fits and then recommend songs from the same cluster. So let's say that our clustering algorithms clusters like this. It makes 2 clusters. For instance, on the left side, there are like more danceable songs, and on the right side, there's not. Then we can look at a user's music taste. Let's say that this green circle is the user's music taste. Then we can like represent or recommend songs that are close to his taste. Okay, so the first algorithm of today is going to be K-means. How many of you guys have worked with K-means before? Okay, so there's some people that have done that. Based on absolutely no empirical evidence, K-means is probably the most used clustering algorithm out there. K-means clustering aims to partition n data points into k clusters, in which the data points belong to the cluster with the nearest distance. This results in partitioning in the data space into something called Voronoi cells. We're going to show you later. There are many different versions of K-means, where the standard algorithm is actually called Lloyd's algorithm. And Lloyd's algorithm is actually so standard that many people just call that for K-means. And it's going to be Lloyd's algorithm that we're going to go through today. So Lloyd's algorithm starts by selecting k centers, which is going to be the number of clusters we want to find. In our example, we can use k as 4, for instance. Just randomly choose a number. Then you repeat 2 steps, assignment and update, until the algorithm converges. The first step, which is the assignment step, is where we assign each data point to the center that is closest to the data point. The second step is to update the cluster centers by recalculating it. And the new value for the cluster center is going to be the average of all data points that were assigned to the cluster center. This then alternates, and hopefully at some point there's going to be no changes in the assignment step, and then the algorithm converges. So let's look at an example here. On the left, you see a data space with a lot of data points, and on the right, you see the error rate, or the average, the sum of average distance between data points and its cluster centers. This works as a performance measure where we want to lower this error. So the first step is to, we chose k equals to 4. So the first step is to randomly just put 4 centers on the map, like this, the 4 white crosses. And then you assign, you do the first step, you assign all the data points to each cluster center. Yeah, so you see to the bottom left in the blue area here, all of the data points are then connected to its data center. Now that was the assignment step. Now you have to do the update step, which is you calculate the average of all the data points in each cluster, and then you move the center where this new value is. So in this case, we're going to move all the centers to the average, which is shown here right now, and then you reassign all the data points over again. And then we have done one iteration of the K-means. Now we're on the second one. And then you assign, and then you recalculate. And then this goes on until there's no real change in the assignment step. And we can see that the average distance within each cluster is decreasing. So let's look at a GIF here. You can see it gets closer and closer, and suddenly it makes a big jump. And it finds the 4 clusters pretty well. Yeah. That was an example of a good run of K-means. But I want to show you another run that doesn't really go that well. Because K-means only finds the local optima and not the global optima. This means that how we initialize the 4 centers in the start actually matters quite a lot. I'm going to show you another convergence in local optima, where the performance is a little bit worse than in the first example. Let's see. There we go. So if you randomly initialize the 4 cluster centers, the algorithm might just find the local optima that is not really any useful. So there are different methods of initializing K-means, and today we're using something called K-means++ that scikit-learn already has made for us. So some advantages of working with K-means is that it works well with large data set and circular shapes, or shapes that has a defined area. Because as we saw, all the space got kind of they got put into a Voronoi cell, and the Voronoi cells are gonna cover the entire data space. So if you have other shapes that are not like kind of circular, it's not gonna work that well. It's also pretty simple and it's inexpensive. Other clustering runtimes are usually larger, making K-means a lot of the times kind of good enough. And it's often used as a kind of first experiment kind of algorithm. Some weaknesses: it doesn't really handle outliers and noise very well. So as we saw, the Voronoi cells is going to cover the entire data space, which means that it's never going to find any outliers ever, because all of the outliers are still going to be in some Voronoi cell. It's always going to belong to some cluster. As I said, non-circular shapes doesn't really work. If you have like a long curvy data set or something, it's not really going to work that well. It gets stuck in a local optimum, like I showed you guys in the second figure there. And another problem is that you need to choose the K, or you need to choose how many clusters you want, which is not always that easy. Sometimes you actually just want the clustering algorithm to tell you how many clusters the algorithm thinks you should have in your data. Yes, so let's show this. So now we're going to choose the same features, that's fine. We're going to put in some classical songs here so we can better see what's happening. And then we are going to run clustering. And it's pretty simple. This is all the code. that we're having. You get the audio features from all the likable songs. We're only going to look at likable songs right now. Then you remove the duplicates because we have multiple playlists that people choose from, and often there are songs that are overlapping, but you only want one of each song. Then you get the real feature values, the song name, and the artist. And then we normalize the data and make sure that everything has the same scale. Then, as we see now, we have chosen like 13 minus 4 features, so we have 9 features here right now. Whoops. So right now we're using PCA to reduce the data from 9 features to 2, so that we can visualize it in a 2-dimensional space. And then we're going to run the K-means. And K-means is basically this code. Here you find the decision boundary, what we're using for plotting. This is how easy it is to just use scikit-learn with K-means. Yeah. So in the first run, I'm just going to leave the number of clusters that we want. This is the K value. I'm just going to leave it at 1, just so we can look at the data a little bit here. So this is how all our likable songs are spread out in the data space. So when you hover over some data points here, you can see their name. And hopefully, the similar kind of songs should be quite next to each other. So here you see some Judas Priest, Ozzy Osbourne, Bruce Springsteen. I don't know if you guys know all of these songs, but Rammstein, Blink-182, and so on. And then we can go further down here, so it's kind of like rock songs over here, I guess. And Hathaway, What is Love? Marilyn Manson, Guns N' Roses. It was kind of a rock song cluster over here. So hopefully, over here, there's going to be some classical music. And it looks like it. Looks like it is as well. So, kind of, you can see that, right? Yeah. So on the right side here, we have more like of a classical music cluster, and on the left side, we have like a rock song cluster. So hopefully, if I say that I want 2 clusters, then it should probably split the classical music songs and the rock songs. Which is also what it does. Yeah. So here you can also see the cluster centers. I don't know how easy it is to see. One of the cluster centers right here, and the other one is over here. Yeah. Yes. I think that was it. Yep.
We're gonna do one more clustering algorithm before we have a break, so just stay on a little bit longer. Really like this picture, actually. I find it really cool. So dbScan stands for density-based spatial clustering of applications with noise. It's a terribly long word, so we're just gonna refer to it as dbScan. It's a well-known clustering algorithm that is commonly used in both big data and machine learning. Based on a set of points, dbScan groups together points that are close to each other based on a distance measurement and a minimum number of points. It also marks outliers, the points that are in low density regions, unlike K-means. So the dbScan algorithm basically requires 2 parameters. You need the EPS, which is the minimum distance between 2 points. It means that if the distance between 2 points is lower or equal to this value, then these points are considered neighbors. The other one is min points, which is the minimum number of points to form a dense region, which means a cluster. For example, if you set the min points parameter as 5, then we need at least 5 points in order to form a cluster. If you take a look at this picture, we see that dbScan managed to form 2 clusters, which I find visually appealing. Doesn't mean that the data means that it's good. It also managed to find a couple of outliers in the middle. The parameter estimation is a problem for many machine learning algorithms. To choose good parameters, we need to understand how they are used and have at least a basic previous knowledge about the data that will be used. When it comes to EPS, if the EPS value chosen is too small, a large part of the data will not be clustered. It will be considered outliers because it doesn't satisfy the minimum number of points to create a dense region. On the other hand, if the value chosen was too high, clusters will merge and the majority of objects will be in one gigantic cluster. The EPS should be chosen based on the distance of the dataset. We can, for instance, use a k-distance graph to find it. But in general, small EPS values are preferable. When it comes to min points, as a general rule, a minimum min point can be derived from a number of dimensions in the dataset, the number of features you include. It should be at least be one larger than this. So if you have 5 features, it should be at least 6. Larger values are usually better for datasets with noise and will form more significant clusters. But why use dbScan? The dbScan algorithm should be used to find associations and structures in the data that are hard to find manually, but that can be relevant and useful to find patterns and predict trends. dbScan are commonly used in biology, medicine, social science, marketing, and so on. For us, we think that dbScan can be great at clustering our music taste, finding out what songs are familiar, and much more. So if you look at this figure, we see the performance of dbScan on the right and K-means on the left. Visually, for me, it looks like dbScan performs better. Some of you might now be thinking, okay, so when should I use K-means and when should I use dbScan? That is a really tough question to give a great answer to in general, but if you look at the advantages of dbScan compared to K-means, it is that you don't have to specify the number of clusters in advance. Also, dbScan can find arbitrary shaped clusters like this. It can even find a cluster completely surrounded by but not connected to a different cluster. The disadvantage of dbScan is that it's difficult to find a good value for EPS, especially for high dimensional data. Also, dbScan cannot cluster dataset well with large differences in densities. But that's enough theory. Let's try to find good values of EPS and see if we can create a great cluster. All right, so we're basically going to use the same approach as with K-means. We're going to exclude K-means and instead include dbScan. The dbScan is, as with the previous algorithm, really easy to set up. You have a method here. You specify the EPS and the minimum number of samples. So if you take a look at the feature set we were using here, we have, as Malte mentioned, 9 features, which means that at least we should have min samples of 10. When it comes to these EPS value, there are ways that you can be helped to find it. But for right now, we're just gonna try and see what happens if you have an EPS of 0.15. All right, so we got 7 clusters. They don't really make much sense. Most of the data are considered outliers. I would guess that this EPS is too small. So it's good to start with small EPS, but you have to bump them up when they don't perform. So let's say if we double it and set the EPS to 3. All right, now it's getting a bit closer. It forms two clusters, one huge one over here, which is still classical music, but it marks a couple of outliers. For instance, it says that whatever this song is not close enough to the majority of the classical songs. Similarly, it's created a cluster of rock and metal songs, but those that differ largely to the other songs are considered outliers. And this is a powerful tool sometimes to be able to say that this song should not be in the same cluster even though it's in the same region. But let's see what happens if we put EPS to a large value. Now, everything is just one cluster, which makes no sense, especially considering that you still have a few outliers. So you can come a long way with dbscan if you have some knowledge of your data and just try different values of both EPS and minimum samples. Another thing you can do is try to increase the minimum samples to see how the data responds to that. Then you require more points to be considered neighbors before they form a cluster. If the EPS is too large, it won't matter. But with smaller EPS, it will hopefully make a difference. Yeah, more or less the same result for this one. That's what we were planning to have before the break. So I suggest we take half an hour, meeting back here at 3 o'clock. That's 34 minutes. So enjoy your coffee, and we'll see you soon.
Okay, I hope everyone had a nice cup of coffee. We're going to introduce one last clustering algorithm before we go over to the classifiers. The algorithm is hierarchical clustering. So the hierarchical clustering starts with that you treat each data point as a separate cluster. Then you repeatedly identify the two clusters that are closest together, and then you merge these two clusters. And then it's done when all clusters are then merged together. We can look at one example here, where we have the data space on our left. We have 6 data points, A, B, C, D, E, and F. And then we have the dendrogram, which is the output of the hierarchical clustering algorithm on the right. So first, we make sure that each data point is its own cluster. So we now have 6 clusters here right now. And you start by merging the 2 clusters that are closest together. And the closest data points right here are probably going to be E and F. So E and F are now a cluster. So now there are 5 clusters. And then you just continue to do this until everything is clustered into one cluster. When there are multiple data points in a cluster, you usually just take the average, like we calculated the K-means centers, and you use that as a starting point of the distance. So the 2 next ones that are going to get merged are probably FE and D. And then the next one is going to be A and B. So now we have 3 clusters. AB is a cluster, C is a cluster, and D, E, and F is a cluster. The dendrogram, also we can see that it tells when all the points got clustered together. So you can kind of derive some useful information out of that. So this goes on until everything is one cluster. Now you can basically just cut anywhere in the dendrogram, like the green line here is showcasing. And then it's going to tell you, show you the 2 clusters. So since we're cutting horizontally here, and we cut over 2 lines, it means we're going to have 2 clusters. If you want 3 clusters, you just move 1 step down. Some advantages of hierarchical clustering is that it outputs dendrogram, which is sometimes pretty useful. You can get a lot of good information from that. It's also a really, really simple algorithm, and it's easy to understand, and it's easy to do. However, it has some weaknesses as well. It's pretty high in time complexity. Every time you add like a data point, you have to always calculate distances between new clusters. And it really rises in complexity when you add new data points. There's also no object swapping between the clusters. When a cluster is assigned, when a data point is assigned to a cluster, the data point can never leave that cluster. So for instance, in the K-means, you could have, in one iteration, a data point that belonged to a certain cluster, and in the next iteration, it could change that it belongs to another cluster. It's also not so good at catching missing data, because it has to cluster all the data at the start of the algorithm, so it's really bad at handling missing data. Another thing is also pretty bad at outliers, because say if you have 1 point all the way over here and you have 100 points here, then it's going to cluster all the data points over here before it then merges the outlier. And then if you want it to output, say, 2 clusters, it's going to output the one outlier over here as one cluster, and then the whole big cluster over here as one cluster. While what you usually want is that you want the algorithm to tell you that, oh, this over here is probably an outlier, and the big clusters then get clustered into 2 different clusters. Okay, let's show you this algorithm. So it's the same code, just comment in the agglomerative hierarchical, as some people call it. Also really easy using scikit-learn. And there's also only one parameter we have to change. Here we see that we're using the Euclidean distance measuring to measure distances between data points. So we can try to run this. Now we run with one cluster, so we get all the data clustered together. It's good. It's exactly the same as last time, with all the classical songs over to the right side and all the kind of rock songs over to the left side. Yeah. Let's see if it can cluster classical songs from rock songs. Let's see if it gives the same result as K-means, for instance, and dbScan. Yeah, it worked pretty well. Can you see that? Yeah. It's a yellow color now. So it works pretty well. Bohemian Rhapsody together with classical music. I don't know about that, but U2 with or without you, sure. Yeah, let's try 7 clusters. So we have one cluster up here. Motorhead out of space, Aerosmith, Def Leppard. We have one cluster here, one down here, Whitesnake over here, and then the yellow ones over here, and 2 over here as well. Cool. I wanted to try to do a really high number. I'm not really sure what's going to happen, but we can try. I don't know, is this 30 clusters? I can't really tell between the coloring, but yeah, looks decent. Yes, cool. So that's it for clustering. Yes.
How important is the reduction you made? Because you reduced it to plot on 2 axes, right?
Mm-hmm.
So how important is that factor here? Can you show us a difference when you plot it differently?
Yes, we're gonna do that, but some time constraints didn't have time. But it is very important. It's also a good point that when you start with a set of variables and then you reduce the data into a lower dimension, like we do from 13 to 2 or 9 to 2, then you might lose some important information in that process. And it's important to not only use your machine learning algorithms on the newly created data set, but at least try it on the raw variables as well, because the raw variables can actually sometimes just perform better anyways, because when you reduce dimensions, you potentially lose important data. Yeah, so it's a good point. Yeah. And that is it for clustering. Clustering in recent years has become a little like the ugly duckling of machine learning, because the support vector machines and neural networks is like shown really good results, so they're like more used. Yes. And that is it for me. Yes.
So everything we've been looking at up until now has been unsupervised learning. So now we're going to add those labels to the mix and do some supervised learning. And the first algorithm that we're going to take a look at is the support vector machine. The SVM is a model which has fallen a little out of favor under the hype of deep learning in recent years. However, it can still be viewed as an effective algorithm, especially when you have limited amount of data. So let's take a look at how it works. Say we have a set of samples from two classes, and they can be described with two features. So now we've plotted these samples onto the space composed by these two features. An SVM will find a hyperplane to divide the two classes. A hyperplane is a subspace consisting of one dimension less than the ambient space. What this means is that in this two-dimensional space, the SVM will find a one-dimensional hyperplane to separate the classes, otherwise known as a line. There are many different hyperplanes that can separate this set of data points. So we could draw an arbitrary line that perfectly separates the points like this. However, you see that this line is a lot closer to the x's than the circles. And this could affect the robustness of the classifier, because the likelihood of misclassifying an x is larger than it has to be, because the decision boundary line is pretty strict. So any hyperplane won't really do. We want to find the most optimal one. The points closest to the hyperplane are called support vectors. So the samples which are close to these two lines, they're support vectors. We find the most optimal hyperplane by maximizing the space between the support vectors and the hyperplane. And this space is called the margin. So we can draw a new hyperplane now, which has a little less of a strict boundary line. So this hyperplane perfectly separates these points, meaning that the data is linearly separable. For more complex problems, your data might be nonlinear, like shown in this graph. There is no way you can separate this set of points from these two classes with a line. To handle such problems, the SVM can be kernelized, meaning that you take these points, these low-dimensional data points, and then you map them out to a space of higher dimension, like this. So now you can use a two-dimensional hyperplane to separate the set of points from the two classes. So before looking at the code, I want to talk about splitting the dataset. When training certain machine learning algorithms, it's usual to split the dataset into a training set, a validation set, and a test set. The training set is used to train the machine learning model, while the validation set is used to control how well the model is able to perform on data the model has not seen before, data that the model does not use for training. So if the performance on the training set is a lot higher than on the validation set, you get the phenomena of overfitting, which I believe Malte talked about earlier. So when your model is overfitting, it means that it's learning the training set more and more, and at some point it just gets better at the training set, but everything it learns is not useful for predicting unseen data. It's not good for generalization. The validation set is not used for training, but it does have an influence on the way you train your model, because you optimize parameters to get better results on the validation set. That's why you have a separate test set, which is used to control the performance of the model on data which is not used in the training process at all. So with a rather small dataset size, we decided to use approximately 80% for training, and then 10% for validation set, and another 10 for the test set. All right, let's take a look at the code. All right, the first thing we're gonna do is we're just gonna remove the classical songs. I don't mind classical songs, but just not today. Also, we're gonna put back all the features. So we're gonna use all 13 features of songs in our classifier. So the first step is pre-processing the data. So we're loading up the likable songs and also the songs that we don't like. We're calling them the annoying songs. Since this data set is constructed from different playlists, there is a chance of the same song occurring in multiple playlists. So the first thing we do is we just remove all the duplicates. Then we filter out only the features of the songs. So we remove like song name and metadata like that. So here we now have a list where each entry in the list is the features of a song. Now we're dealing with supervised learning, so we also need the labels. And we're labeling the likable songs with a 1 and the annoying songs with a 0. They have to be numbers so that the model can understand what's going on. Then we put everything into a NumPy array, the data and the labels. We also talked about normalization earlier. We want the data to be on the same scale, so we normalize the input data, and then we split the data into the training set, the validation set, and the test set. So moving down to the SVM training method. We're using scikit-learn, and it's just like with the clustering methods, it's really easy to get a model up and running quickly. It's basically just 2 lines of code, and you got a trained model. So we train the model on the training set, and then we run the validation set through the trained model, and the same thing can be done for the test set. So the validation accuracy now of the SVM is 86%, and the test accuracy is a little bit lower, 82%. So the accuracy is a performance metric which tells us that of all the data that was sent through the model, it managed to correctly predict 86% in the validation set. And this performance metric essentially tells us that this model, given a song, can with an accuracy of 86% tell us if we will like the song or not. So I'm not going to spend too much time on training the model before we move on, but at this point we could also try out just removing features and see how that affects the model, right? So if we remove duration, then the performance is actually a little bit better on the validation set and a little bit worse on the test set. So usually the performance on the test set and the validation set should be pretty similar, and if it's not, it could be that the data set is a little bit uneven. Because when we split the data set, we just shuffle the data set, and the distribution should be pretty similar in all splits. So if we comment out the energy, let's see what happens then. So at this point, the validation set and test accuracy are getting a little bit closer. There are also other parameters that can be tuned for the SVM. For example, the slack variable, which is a value that if you have a data set that is not linearly separable, you could have a lower slack variable, which means that you're going to allow for some training samples to not be a part of like not be separated along with the other training samples, if that makes sense. So you're giving the model a little bit of slack and allowing for errors, which could also help as a regularization method, because regularization are just methods that counteract overfitting. So if you have a lower slack and allow for errors, it could be that your model will perform actually better on unseen data by not focusing too much on the training set. But for now, we're just going to move on to the recommendation system. So our recommendation system is pretty simple. What we've done is we trained the SVM, and then we store the model. And then, as we talked about earlier, we're using a very large playlist to simulate the world of songs, because we don't really have access to all the songs in the world. So we're just using a playlist that contains approximately 8,000 songs. And then we process this playlist as we did with our dataset. We remove the duplicates. Then we also remove the training set tracks from this playlist so that the recommendations do not contain the same tracks. We load up the model. We normalize the world songs playlist data. And then we just run this playlist through our model. And what we get then is a probability for each song in this playlist of how likely it is for us to like this song. And then we just sort out this result by likability. And then we pick out, say, 30 songs from like the 30 top scoring songs. All right, so as you remember, our likable songs list contained a lot of rock songs for the most part. And here in this list we see Aerosmith, Stone Temple Pilots, Led Zeppelin, ZZ Top, Guns N' Roses. You know, a lot of rock songs. And these songs are not in the training set. Our model has never seen these songs before. So all these recommendations, it's based on the training set and similarity of songs. And yeah, this song, I have no idea what this is all about, but sure. Just for the sake of it, we've also plotted out, listed up the songs that the model thinks we won't like at all, right? The lowest scoring songs. And as you remember, in our unknowing songs list, we have a lot of songs under hip-hop, R&B, electronic dance. And here we see that you have rap songs, Dr. Dre, Eminem, GEC, Iggy Azalea, Snake Ships. So this fits the profile and how we train the model. I think that's enough said about the SVM, and I think we'll move on to neural networks. So we've been hearing a lot about neural networks lately, mostly under the buzzword of deep learning. Due to the greater access to computational power and the amount of data, we've seen remarkable results with the use of deep learning in recent years with regards to image recognition and speech recognition. How many people here have worked with neural networks before? Okay, there are some. Not quite a lot. That's fine, because for the next 10 to 15 minutes, I was thinking about, or I'm going to explain a little bit in more detail how neural networks work. Because to construct a neural network, you need to understand it a little bit more than just a black box. It's not quite just 2 lines like we could do with the SVM. So I thought I'd break down the black box of neural networks with some simple examples before digging into the more intricate details. So let's use yet another car analogy. It's easier to understand, so we're using a lot of car analogies today, I guess. So now this can be viewed as a very simple neural network. We only have one input variable, the engine power of the car. And then we have a prediction of price as output. The circle represents a neuron. Naturally, neural networks consist of neurons, as following an analogy of how neurons in the human brain processes information. This neuron executes some kind of function on the input to predict the price of the car. Let's expand further. So by intuition, we could say that the engine power of a car and the weight of the car can tell us something about the speed of the car, right? If a car is heavy, it's probably slower, and if the engine power is higher, then it's probably faster. Furthermore, given the seat fabric in the car and the amount of leg space, it tells us something about the level of comfort that the car provides. We can say that these 2 inferences, they're high-level abstractions that the network might be able to learn. So by putting this together, we get a neural network with multiple layers. Through multiple layers, a neural network has the potential to learn the relationships between the inputs from one layer and infer high-level concepts which it can pass on to the next layer. So given the 4 input variables, the network may infer information about the comfort and speed in a car, which then again narrows down the process of estimating the price of a car. This is the input layer. The number of neurons in the input layer corresponds to the number of features used to describe one instance of data. So if we use seat fabric, leg space, and engine power, and weight to describe a car, then we have 4 input features, so 4 input neurons. No processing is done in the input layer. The input basically just passes through. The number of neurons in the output layer really depends on the type of classifier we're training. So in this illustration, we have a regression problem. So the output is a continuous numerical value. So we only have 1 neuron. But for classification problems, where we want the model to predict a specific class, we would typically have 1 output neuron for each class. The layer in the middle is called a hidden layer. A network can have an arbitrary number of hidden layers and an arbitrary number of neurons in each layer. Finding the optimal values is a part of constructing the network for the best results. Now, I mentioned how SVMs can be kernelized to handle nonlinear problems. The hidden layer is essentially what lets the neural network do the same thing. In reality, the hidden layer looks more like this, because the high-level abstractions that it learns are not visible to us. We can just hypothesize about what it learns. This is why it's called the hidden layer. We don't really know what's going on in there, which is also why we have to make this figure a little bit more chaotic. Since we don't know what kind of concepts the network can learn, we just feed all the neurons in each layer, every neuron in the previous layer. And then we just cross our fingers, almost. Let me give you an overview of the training process of a neural network. So before anything else, you initialize the weights and bias with random values. So in a neural network, you have two sets of parameters. You have the hyperparameters and you have learned parameters. The hyperparameters are values that you choose as you construct the network. For example, you have the number of hidden layers and the number of hidden neurons. The learned parameters consists of the weights and bias. The entire goal of training a neural network is to find the most optimal values for these learned parameters. They represent the variables the model learns, and they're used in the target prediction function in the end. And that's why these parameters, they just change during training. Then our repetitive process starts, where you start out with forward propagation, which is where you take your training set and you feed the neural network the training set to get predictions. Then you can use these predictions to compare with the correct labels, and then you compute the error rate, or the loss, as we call it. In the back propagation step, the error is passed back to the neurons of the network. And then the weights and the bias, they're modified appropriately in an effort to decrease the loss, the error. And this process repeats. Let's take a closer look at each step. So for each training sample, we have 4 input variables, right? And each neuron connection is associated with a separate weight parameter, like this. So don't mind the subscripts, they just describe which input neuron is connected to which hidden neuron. So these weights are, they connect all the input variables to the first hidden neuron. Then you also have a separate set of weights which connect the same input variables to the second hidden neuron. So let's take a closer look at what happens in a particular neuron. So when a training sample is sent through the network, the neurons transform the inputs by first calculating the sum of input weight products. It looks something like this. This expression can be rewritten to something like this. And then we add a value called the bias. This is also a parameter which is learned by the model. The bias works as a form of threshold for the neurons, making it either harder or easier for the neurons to activate for the features that each neuron learns. Thus, the bias essentially makes the neurons more flexible. Furthermore, each neuron applies a function on the result of this. This function is called the activation function. And choosing the right function is a part of the neural network architecture. In the remaining neurons, we have similar calculations with their own set of weights and bias. During training, these neurons learn different patterns or features of the data, and together this makes the basis for the prediction output. So let's talk about how the network learns. During the training, we want to monitor the error rate. And for this, we use a particular loss function. So, for example, say we send a sample of a car through the network, and we get a predicted price of 60,000 euros. Then it turns out that the correct price is actually 80,000 euros. Now, an intuitive loss function would perhaps be, just taking the difference. It's understandable for us, right? But there are other functions which have better mathematical properties, so I usually use one of those. For example, the mean squared error function. You just compute the squared error, and then you take the average of this. The type of loss function usually depends on the problem and the architecture of the network. So when training a neural network, the goal is to find the most optimal values for the weights and bias, right? So after an iteration of forward passing the training samples, these parameters have to be changed so that we can move towards minimizing the loss. This is why we use a gradient descent-based optimizer. Gradient descent is an algorithm used to find the minimum of a function. And the general idea is that to decrease the value of the loss, the partial derivatives, or the gradients, of the loss has to be calculated for each learned parameter, with respect to each learned parameter. The gradient essentially tells us how much we need to increase or decrease the parameters to go towards the minimum. So now we can use the gradient to update the parameters. So you just subtract each parameter with the corresponding gradient, which is also scaled with a constant called the learning factor. You want to scale the change, how much you change it, because if you change the values too much, you might skip past the point where the loss is at the minimum. So this is an iterative process where you just want to change carefully and move towards the minimum. It's kind of complicated to explain this, but I hope you guys understood something. So the entire process I just described repeats many times. The entire training set is fed to a network many times until the network is unable to improve. So the network that we've been looking at now is called a feed-forward network. There are other types of networks as well, but we're not going to go into those today. So before we take a look at the code, I just want to do a recap of some terms and add some others. An epoch is one round of feeding the entire training set to the neural network. So typically when training a neural network, you will run for several epochs, many epochs. The activation function, as I talked about, there are different activation functions, but lately the go-to function in the hidden layers has been a function called the rectified linear unit, the ReLU. It's just a function that gives you the maximum of 0 and the input value. So it eliminates negative values. In the output layer, we're going to use the sigmoid function. Sigmoid is a function that squashes the input down to the range between 0 and 1. And this is perfect for our problem of classifying which songs we'll like, because if the output is close to 1, it means that we like the song. If it's close to 0, we don't like the song. Again, the loss function used to estimate error, and the optimizer, the gradient descent-based optimizer, is used to update the weights. So let's look at the code. So the data pre-processing step is very similar. It's basically the same as we did for the SVM. But there's a little bit more code, not a lot, but a little bit more code than we had before. So we instantiate the model object with a sequential object. It's a Keras wrapper object. And to this object, we add layers of the neural network. So this is the first hidden layer. And the input layer is basically programmatically just embedded in the first layer, the first hidden layer of the network. So in here, we specified the dimension of the input layer. So since we have 13 features, we're just going to get the length of this list, and the input dimension is 13. Right now, we just have one neuron in the hidden layer, and we're using the ReLU activation function. Then the output layer consists of one neuron, and we're using the sigmoid activation function to get a value between 0 and 1. Furthermore, we use the binary cross-entropy loss function, which works out well for binary problems using the sigmoid function. And then we use the Atom optimizer. It's a gradient descent-based optimizer. It just does some extra stuff that I'm not going to get into now. The next step is to train the model. So we pass the training set and the labels of the training set to the model. We also give it the validation set. The batch size is the number of training samples you want to run through the neural network before you do a parameter update of the weights and bias. So keeping a low number here can have a regularizing effect because you do frequent updates so that it's less likely to overfit to the training data. This is the number of epochs, the number of times we want to run the training set through the network. Then we also shuffle the set after each epoch. All right, I think we're ready to go. So now we're just training it for 150 epochs. My interface is a little bit bugged because it's not supposed to print all these lines. It's just supposed to print one line per epoch, but yeah, sorry about that. So this graph tells us it gives us information about the training process. So for each epoch on the x-axis, we get the validation loss, the loss on the validation set, along with the loss on the training set. We also get the training accuracy and the accuracy on the validation set. So with only one neuron in the hidden layer, we already have an accuracy of approximately 85%. So the way we pose this problem is it's not really that complex, and the training data it's not a lot of data. And we also see that the loss curves for the training set and the validation set, they're pretty similar. They follow the same curve, which means that our model is not really overfitting, which is good. But we also see that after approximately 60 epochs or 40 epochs, or let's look at the loss instead. After approximately 100 epochs, it doesn't learn a lot more from the training set. We also see that the training accuracy stops at around 85%. So we want to see if we're able to make the model a little bit more complex so that it can perhaps learn more. So what we'll do is we'll increase the number of hidden neurons in the hidden layer. So let's overdo it a little bit and just add 100. So what we see now is that the training accuracy is actually above 90% now. So it's extracting more information from the training set. But we also see that before even 10 epochs, it's starting to overfit. So the loss on the training set, it's decreasing for every single epoch. It's even decreasing still after 150 epochs. But the amount of loss on the validation set, it's actually starting to increase. And this is a sign of extreme overfitting. This means that the model can probably perfectly fit the training set at some point. But if you show it unseen data, it's not going to perform well. So let's counteract this by adding some regularization methods to counteract overfitting. So what we're going to do is we're going to add dropout to the hidden layer. Dropout is a method where you, for each iteration, you just deactivate a certain percentage of the neurons. What this does is that you simulate using several networks to train on the same data. So we're going to use a high number, 50%. So we're deactivating 50% of the neurons in each iteration, and we'll see what happens. So as you can see, it's not overfitting as much as it did. It is still overfitting, as you can see here, but it is counteracting some of it. What we can also do is add something called early stopping, because now we're training for 150 epochs, but we see that after, say, 40 epochs, there's no real reason to train further, because it's actually just, the model is being destructive. It's learning features that are not useful. So we add early stopping. And early stopping will monitor the validation loss in such a way that when the model stops improving on the validation loss, the training process is just going to stop overall. So now, after 20 epochs, the training just stops, and we see that the curves are a lot more, that they're following the same line. So 100 neurons is probably a little bit of an overkill for a feature set of 13. So we're just going to reduce it a little bit, and before I show you the recommendations that it can pull out. This is fine. So the recommendation process is the same as before. We were just running that big playlist through the model, and then we can have a look at the recommendations. So this list contains some other songs than what the SVM predicted, but it's still a lot of rock songs, as expected. And also in the list of songs that we won't like, we also have hip-hop, rap. All right, let's get back to the presentation slides. So when working with machine learning, there's no such thing as the best algorithm, right? The performance of each algorithm depends on factors such as the complexity of the problem, the number of training samples available, and the number of features in the data. The best way to know is through trial and error, but it can be useful to know some pros and cons about different algorithms to help you along the way. So let's compare the SVM and the neural network. With regards to dataset size, we can say that to leverage the power of neural networks, you usually need a lot of data at your disposal to avoid overfitting. On the other hand, SVMs can work well with smaller datasets, but it doesn't really scale as well for larger datasets because the training complexity of SVMs increases with the number of training samples. And we have seen that given a large amount of data, neural networks have proven to be superior at modeling complex nonlinear problems. SVMs do have fewer hyperparameters, tunable parameters, than neural networks, so it requires less time searching for well-working parameters. With neural networks, choosing the right hyperparameters can have a big effect on the learning process, and choosing the right architecture, it is time-consuming. But in return, you can potentially spend less time on feature engineering, which we've talked about earlier, because neural networks are good at capturing the relative importance of features and the high-level concepts from them. With that said, it's really expensive to train large neural network models. You probably heard that you usually need GPUs, TPUs to train large neural network models with a lot of data.
All right. Have you learned anything today? One guy is shaking his head. That's good. So I'm just going to give you a quick summary of some of the things we talked about. We started out by introducing some core concepts in machine learning, touching by subjects like features, labels, and feature engineering. We explored a Spotify dataset, going through the API and talking about their features. We also had a demo showing what basic statistics could do without any machine learning, trying to see if you could get anything interesting out of the data without using machine learning. And finally, we started with real machine learning, with an introduction to supervised and unsupervised machine learning, before exploring relevant clustering algorithms. We took a look at K-means, DB-scan, and HIERARCHICAL, looking at the advantages and disadvantages of each of them, showing how they responded with the dataset. We used these classifiers to see the underlying structure with both the songs themselves and your music tastes, trying to find similarities. Then we explored a couple of classifiers in order to predict which songs you would like and which songs you would not like. We just explored the SVM and we finished off with the neural networks. And finally, we present our music recommendations. I don't know if the recommendations were great, but they were at least decent. We got rock and roll and not hip-hop, so that's good. When I talked about the agenda at the very start, I mentioned that we will finish off by talking about how Spotify have created their Discover Weekly, and that's what we're going to do now. So just to remind you, we are not from Spotify. We have never worked for Spotify, so what we present is what is common knowledge on the web. So Spotify analyze audio output in order to create vector representation of songs. So kind of what we did with their API, making songs comparable to each other. They use conventional neural networks for this, which is a form of neural networks that traditionally has been used for images, but lately has been found to have more areas where it's useful. The first step involves a lot of data, way too much data for this poor computer to handle. They will analyze all playlists in the world, more or less, trying to find similarities between playlists. So if you have a song that you listen a lot to, and there are another person having that song in their playlists, and this particular players also have a few songs that you don't have, but is in your core music taste, then it's interesting to recommend you these songs. Or said in a different way, they try to find playlists with your tastes and find songs in those playlists that you probably don't know. Spotify also uses collaborative filtering based on usage data. Basically, all interactions you do with songs on Spotify are logged. If you play a song or add a song to your playlist, it's logged. In the same way, if you skip a song that was in your Discover Weekly, it is logged. This way, Spotify profiles your music taste and can compare your profile with the music profile of other users. This is much the same as Netflix uses for their video recommendation systems. The next step is to use the music profile they have created for you. They will try to cluster your songs and your listening behaviors into clusters. These clusters are usually very specific. So instead of having just pop and soul, they're more likely to have synth pop and southern soul. Spotify also uses deep learning and neural networks, as we did, in order to give good recommendations. So if you explore this figure that we found on the Great Web, it's a visualization of how a person's music taste could look like. The darker fields are the core music taste preferences. So in this figure, that's funk, soul, indie, folk rock, and folk. Now, they will typically try to recommend songs that are from one of the darker fields. Also notice that this figure have an outlier, a dot outside a huge cluster. That's a children's song, and Spotify understands that this music is not part of the user's regular music taste. Similarly, they will mostly exclude periodic patterns, so if you during Christmas listen a lot to Christmas songs, it doesn't include in your music profile. So when they create your Discover Weekly, they combine these two steps. They have a model of all the music that exists combined with the knowledge of how users create their playlists. And Spotify have a model of your music taste. They combine these steps, add a little magic filtering, and try to find songs that other users have heard that's similar to your core music taste, but you haven't listened to or is relatively unknown for you. When we were doing research for this talk, we got a few sites giving recommendations on how you can improve your Discover Weekly playlist on Spotify. And basically, that's just keeping in mind that they log everything you do. So if you add songs to your playlist or listen a lot to songs, they're going to consider these songs like likable songs. If you skip a song, they would say that that's a bad sign, you don't like that song. If you explore songs, checking out the artist profile or similarly, Spotify will judge that song as a particular good song for you. So if you don't like the Discover Weekly today, you can just be patient and listen to what you like, and it will hopefully become better. So hopefully you have all learned something here today. It's been really interesting for us to be here. If you have any questions, we are here after the talk, so you can come down and talk to us. And I hope this has been an inspiration somehow for you to start working with machine learning. Thank you for all for showing up and listening to our presentation.